Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So today I will discuss about simple stresses and strains. In this module, I want to discuss about lateral strain, linear strain, and elastic modulus and modulus of rigidity and volumetric strain. So, and then we will see the relation between these three, E and C and K constants. We will see. Already we have studied about stresses and strains and how many types of stresses and strains are there in previous session. So this is our second lecture. Simple stresses and strains. At the end of the course, the students should be able to learn, explain the concepts of stress strain, material constitutional relationship, and then strain energy induced in a linear, elastic, or homogeneous and isotropic materials subjected to forces. So we are discussing the CO1. So already we have learned the stress strain concepts and the relationship, the material constitutional relationship we will see, and then strain energy, and then the component subjected to some forces, how to calculate the stresses and strain and these constants we will see later. So coming to the CO2, illustrate the shear force and bending moment distribution. So first we will see the calculation of shear force and then the bending moment and then shear force distribution and the bending moment distribution in the various beams for analyzing the structural behavior under various loads. So next, CO3, analyze the theory of simple bending for illustrating the distribution of bending stresses across the section beams under loading. Simple bending theory we will discuss for illustrating the distribution of bending stresses. And CO4, make use of the maximum shear stress and shear stress distribution across the depth of symmetric and unsymmetrical beams. So loaded with various loads for the safe design of aircraft components. Next, CO5. In CO5, utilize the Maxwell reciprocal theorem, double integration method, and the moment area method for determining. And the course outcome 6, demonstrate the principal stresses, principal planes, and torsional stresses acting on any arbitrary plane within a structure using analytical and Morse circle methods. So we will learn in this course outcome CO6. So principal stresses and principal planes and torsional stresses whenever acting on any arbitrary plane within a structure. So here we will calculate analytical method and then graphical method. So that is a Morse circle method. So first we will see the CO1, the simple stress and strains. Already in previous session we have discussed about this introduction. When an external force acts on a body, the body tends to undergo some deformation. So due to cohesion between the molecules, the body resists deformation. The resisting force is nothing but strength of the material. So this resistance, which material of the body opposes the deformation, is known as strength of material. So but behind the elastic stress, the resistance offered by the material is less than the applied load. This is called as elastic limit zone. In such case, deformation continues until failure takes place. The deformation will continue until failure takes place. This this phenomena we will observe in a stress strain curve. So within elastic state, the resisting force equals applied load. This resisting force per unit area is called stress or intensity of stress. So already we have seen in a previous session, the resisting stress is equal to load per area. So this is resisting force or F by A. This resisting force and area, unit area, cross-sectional area gives the stress or intensity. The units are Newton per mm square or Newton per meter square. Okay. Next, now we will see the relation between E and C. So what is E? The modulus of velocity or Young's modulus. So already you have learned in Hooke's law theorem. The theorem says the stress is directly proportional to strain. So with the help of the some constants, that is E, you can write like this, E into epsilon. So the E is modulus of velocity. You can write stress per strain. Per strain there is no units and stress Newton per mm square. So whenever the component is subjected to tensile or compressive load, whereas in shear, the modulus of rigidity, that is C, you can write the help of C. C is equal to shear stress upon by shear strain. So now we will see the relation between these three. So first we will see two constants and then third one is volumetric strain and bulk modulus. So you will see in coming up slides. First we will consider a cube of length L subjected to a shear stress of tau. The cube of length L, that is A, B, C, D, the shear stress subjected to shear stress. So what will happen? Some deformation will be occurred in this cube. So you can see the deformation in this figure. Initially the points are A, B, C, D. After that A, P, C1 and D1 and D2. These are the after deformation whenever the component is subjected to shear stress with an angle phi. So a little consideration will show that due to these stresses, the cube is subjected to some distortion. Already I told you. Such that the diagonal BD will be elongated. So you can see the diagonal BD. So initially this is the diagonal. So this diagonal BD will be elongated as B D dash, and the diagonal AC, this one AC will be shortened. So this one is this diagonal elongated. At the same time, what will happen? The C shortened. So C point C1 shortened to C1, but D elongated to D1. This is elongation, and this one is shortened. So this shear stress causes shear strain. So shear strain is equal to how much this elongated to the original strain. Change in length by original length. The diagonal BD is now distorted to BD1. So you can see in this figure. Now calculate the strain of BD. So what is the strain of BD? So BD strain, what is the original length, and then change in length by original length. Now the strain of BD. So see in this diagram, the strain BD1 minus BD by BD. So change in length. So elongated. So how much elongated? BD1. What is the previous one? BD. So subtract, you will get the actual change in length. So as per definition, the strain is equal to change in length by original length. Change in length upon original length. It may be length or diameter. Clear? So linear length or lateral. Any dimension. So now what is the BD1 minus BD? You can write in terms of D1, D2. Take perpendicular line from here D2 on a BD1 line. So now D1D cos 45 is equal to cos 45 upon by BD is equal to root 2 AD. BD is equal to, so take this diagram ADB triangle. ADB. So the BD is equal to, you take 45 degrees. So we can write cos for in terms of cos 45, and then D1D cos 45, and then upon by root 2 AD. BD is equal to root 2 AD. Sin 45 or cos 45, cos 45 is opposite by AD, opposite by hypotenuse. So you know the sin 45 is equal to 1 by root 2. So now D1D cos 45 1 by root 2, substitute here this value 1 by root 2. So 1 by root 2, 1 by root 2 will get 1 by 2. So you can write 5 by 2. So D1D by AD. D1D by AD. So take this triangle D1D and this one. So this one is angle phi. So now D1D is equal to D1D by AD. You can write in terms of angle pi. So pi by 2. So now the strain of BD is equal to strain of AD BD is equal to pi by 2. So D1 due by AD, opposite by adjacent. So tan 45 is equal to 1. So that you will get pi by 2. Next one. Thus, linear strain of diagonal BD is half of the shear strain. So already we have calculated the shear strain, half of the shear strain, and is tensile in nature. Why? Because it is elongated. So that's why tensile nature. Similarly, it can be proved that the linear strain of the diagonal AC is also equal to half of the shear strain. So, but it is compressive in nature. So, in the second one, the strain of the diagonal, the diagonal AC. So, here shortened. Take this CC1, CC1, B. C1C by BC. Clear? So, the shear strain, half of the AC is also equal to the half of the shear strain, but is compressive in nature. Now, this linear strain of diagonal BD, you can write tau by 2C. So, within the elastic limit, the shear stress is directly proportional to the shear strain. The shear stress directly proportional to the shear strain. So, shear strain here pi. Clear? So, the directly proportional, sorry. Now, you can write with the help of C, that is modulus of Young's elasticity. E is Young's modulus, and rigidity in case of shear C. So, C into phi. The tau by C is equal to phi. Okay? So, that's why you can write pi by 2 is equal to tau by 2C. So, let us now consider this shear stress acting on the sides AB, CD, and then CB, and AD. CB, AB, and CD. So, we know that the effect of this stress is to cause tensile stress on the diagonal BD and compressive stress on the diagonal AC. So, effect of this shear stress on AC, and similarly the BD, the diagonal BD, due to tensile stress on the diagonal BD. Now, you can write E is equal to shear stress by shear strain. So, this is whatever applied shear stress, that is due to this shear stress, the diagonal BD elongated and the diagonal AC shortened. So, that's why you can write E is equal to shear stress upon shear strain. So, now the shear strain is equal to tau by E, the second equation. Now, tensile strain on the diagonal BD due to compressive stress on the diagonal AC, tensile strain. So, you know, so the Poisson's ratio 1 by m is equal to lateral strain by linear strain, the Poisson's ratio. So, your lateral strain is equal to Poisson's ratio, you can represent with 1 by m, multiply with linear strain. So, the 1 by linear strain already we calculated in previous slide. So, tau by E, the linear strain. So, that is phi. So, you can write 1 by m into phi, linear strain. That is, you can write it as third equation. So, the combined effect of the above two stresses on the diagonal BD, that is equation 2 plus 3. So equation 2 is tau by E. Equation 3, just now we calculated it. So 1 by m into tau by E, capital E. 1 by m multiplied with shear stress upon Young's modulus. Now take common tau by E into 1 plus 1 plus 1 by m. So tau by E is equal to, you can write m plus 1 by m. So that is fourth one. Now equating the 1 and 4th. The equating 1 and 4th. So what is the 1? The 1 equation is pi by 2 is equal to tau by 2c. So now the tau by 2c is equal to the fourth one, tau by E into m plus 1 by m. This one. So simplify, you will get C is equal to me by 2 into m plus 1. Or 2c E is equal to 2c into 1 plus 1 by m. So this is the relation between the modulus of velocity, Young's modulus, and the shear modulus, that is modulus of rigidity. So that is C. So like this, you have to derive the relation between E and C. Next one, bulk modulus. So when a body is subjected to 3 mutually perpendicular stresses of equal intensity, the ratio of direct stress to the corresponding volumetric strain is known as bulk modulus. So it is denoted by X. Okay. So here, subjected to, in previous case we have seen biaxial stresses. But whenever the body is subjected to 3 perpendicular stresses, so what will happen? The ratio of direct stress to the corresponding volumetric strain is known as bulk modulus. You can represent with K, and you can write the sigma by direct stress sigma by the volumetric strain. So how much volume changed? The change of volume upon original volume. So you will get the K for relation. And finally we will see, so what is the relation between E and C and K? First we will see relation between E and K. So consider a cube ABC, A, B, C, D, A1, B1, C1 and D1. So ABCD is one surface, ABCD, and another one, the backside surface, that is A dash, A1, B1, C1 and D1. Let the cube be subjected to 3 mutually perpendicular tensile stresses of equal intensity. Tensile stresses, sigma 1 tensile stress mutually subjected to in x direction, y direction and z direction. So then what is the relation between Young's modulus and this volumetric bulk modulus? Select sigma stress on the faces, L length of the cube, and Young's modulus E for the material of the block. Now consider the deformation of one side of cube, say AB. So one side of the cube is deformation is deformation, one side of the cube, say AB, under the action of the three mutually perpendicular tensile stresses, this side will affect from the following strains due to the pair of stresses. So the tensile strain along XX cross section, the tensile strain is equal to tensile stress upon Young's modulus or modulus of elasticity. The compressive lateral strain along YY. So 1 by M, so along YY compressed. So you can use here negative sign 1 by M Poisson ratio multiply with sigma by E. Lateral strain along YY in X direction, Y and Z. In the Y direction, compressed. So the dimension will be reduced. So that's why use this relation, and then lateral strain along ZZ. That one also 1 by M multiply with sigma by E. So the resultant strain along XX direction. So here the resultant strain change in length upon original length. That is equal to, you can write the first one sigma by E, that is tensile strain along the x-axis, and then tensile strain, compressive strain along YY, and along Z, lateral strain along ZZ axis. So the resultant strain means the summation of all strains will give the resultant strain of the cube. The original volume of the cube is L cube. So differentiating above equation with respect to L. So dV by dl I will show you. So first write it like this. So finally you will get the summation of strain is equal to sigma by E 1 minus 2 by M. So 1 by M is Poisson's ratio. So that is nothing but lateral strain to linear. It is the ratio of lateral strain to linear strain. Clear? Now differentiate with respect to L, the original volume equation. The original volume V is equal to L cube. So now dV by dl or delta V by delta L, that is change in volume with respect to L. So 3L square. So now write the equation like this: delta V is equal to 3L square into L square into delta L. So now divide and multiply with L. So divide with L, divided by L and multiply L. So we will get the equation delta V is equal to 3L square, 3L cube, delta L by L. So divide with L and multiply with L. So now substituting equation 1 and 2. So now the one equation is delta L by L is equal to sigma by E into 1 minus 2 by M. Substitute in this equation. So now delta V is equal to 3L cube multiply with sigma by E delta L by L is equal to 3L cube into delta L by L. In place of delta L by L, substitute sigma by E into 1 minus 2 by M. So therefore V is equal to L cube. So delta V by V is equal to 3L cube by L cube multiply with this delta L by L. So substitute in place of V L cube. So after simplification, we will get 3 sigma by E into 1 minus 2 by M. So this is a volumetric strain, delta V by V. So now we will find the relation between E and K. So delta sigma by delta V by V. So now you can simplify here, delta V by V is equal to 3 sigma by E, 3 sigma by V into minus 1 by 2 by M. So now we can simplify this equation like this, and you will get K value. K is equal to ME upon 3 by M minus 2. To simplify, or E is equal to 3K multiplied with 1 minus 2. So this is the relation between E and K. You have seen in previous slides, relation between E and C, and C, and then now in this slide you have derived E is equal to 3K into 1 minus 2. What is mu here? The mu is equal to Poisson's ratio. That is in place of 1 by M. You can use mu, the term, the letter mu you can use for Poisson's ratio. So this is the relation between E and K. So now we will derive the relation between E, G or C. What is G? G also modulus of rigidity, or C and K. You can represent with G or C. So you have derived E and relation between E and C, relation between E and K. Now you have to derive the relation between E, C and K, between these three. So we know that the first equation E is equal to 2G into 1 plus mu. So 2G or 2C. Okay, mu is equal to 1 by M. And another equation, relation between E and K, E is equal to 3K into 1 minus 2 mu. So now from one equation, you can write the mu is equal to like this. E by 2G minus 1. 2G or 2C. Don't confuse here. 2C. Both are same. E by 2C minus 1. So equating this value in one equation. The substitute in one equation, E by 2C minus 1, that is mu value in this, substitute in 2. E by 2C value substitute in 2 value, equation 2. Equation 2 is E is equal to 3K into 1 minus 2 mu. So 3K multiplied with 1 minus 2 mu is equal to E by 2G minus 1, that is equal to 3K into 1 minus E by G plus 2. So now you will get E is equal to 3K into 3G minus E by G. Clear? So now after simplification, E is equal to 3K into 3G minus E, or 9 kg minus 3 kE. Easy, go this side, this one, and and Eg plus 3 Ke, now 9 kg, 9 kg. Now you can write this equation like this. Now finally E is relation, we will get E relation between E, C and G. So R E is equal to 9 Kc by C plus 3K. 9 Kc by C plus 3K. This is the relation between these three. So material constitutions relationship. E Mann's modulus or modulus of elasticity or modulus of rigidity and bulk modulus. So next one is volumetric strain. The volumetric strain have seen in previous derivation delta V by V. So what is this volumetric strain? So consider a rectangular body subjected to direct tensile stresses along three mutually perpendicular axes as shown in figure. So here given the rectangular body subjected to direct tensile stresses along three mutual perpendicular. So one is x-axis and y-axis and another one is z-axis. So whenever this one subjected to tensile stress. Now let assume the sigma x stress in x direction, sigma y is y direction, and sigma z in z direction, and E is the modulus of elasticity. The strain in x direction due to stress, the strain stress upon E. Similarly, sigma y in y direction sigma by E, and the strain is equal to in z direction sigma z by E. So the resulting strains in the three directions may be found out by the principle of superposition. So that is by adding algebraically the strains in each direction due to each individual stresses. So now the three tensile stresses shown in figure taking tensile strains as positive and compressive strains as negative. The resultant strain in x direction sigma x, the psi x is equal to the strain in x direction sigma x by E minus sigma y by me minus sigma z by me. So here 1 by m is Poisson ratio. You can Poisson's ratio. So you can write it as with the letter mu. So 1 by E, now take common 1 by E and you will get sigma x minus sigma y by m minus sigma z by m. In x direction sigma x by x E and y direction sigma y by E and z sigma z by E. So already you know. So now in y direction, what is the tensile strain? What is the strain? Now the tensile strain in y direction minus x direction. So this is the tensile strain in x direction negative and sigma z by z also negative. Why? Because in tensile in x direction, in tensile nature elongated. The compressive, that is the dimension will be shorted. So now 1 by E sigma E y minus sigma x by m minus sigma z by m. So similarly z in z strain in the z axis strain sigma z by E minus sigma x by me sigma y by me. So right here again take common. So here we are calculating three tensile stresses. So while you are calculating In x direction strain, use y and z. In y, x and z, and in z, x and y. Clear? So now you will get three relations. For the three tensile stresses shown already in figure, the resultant strain in x direction, the volumetric strain may then be found by the relation delta V by V is equal to the summation of all these resultant stresses, sigma x, epsilon and y, epsilon x, epsilon y, and epsilon z. Total three strains. The algebraic sum of three strains will give volumetric strain. So like this, how to derive the relations between these three. These are called as material constitutional relationships. The Young's modulus C and modulus of rigidity C, and then bulk modulus K. The references have taken the Ramamurtam, the strength of materials, the book title is Strength of Materials, so publication Dhanpati Rai, and Rajput, that is Strength of Materials, and R.K. Bansal, textbook of Strength of Material, and R.S. Kurmi. So these are the references I have taken for preparing this PPT. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.